Okay, just have a look at page 71. Okay, this is page 71. Right? Page 71. A mass on the end of a spring bounces up and down as shown after being released at time t equals 0. Which graph shows how the velocity varies with time? This one, maybe try a minute or two to look through it. Then after that, I discuss with you. Okay.
Okay.
All right. So let me just search for the others that may be useful for you. So this one. One. So no. 2. And 58. So this one here that you're doing for page 71, you can actually divide it into 4 separate sections, like just now also. Okay. So since this is displacement time, it's talking about distance time and velocity time, you would be using this. Velocity is rate of change of displacement. So we say that the value of velocity is equals to the gradient of your ST graph. Right now you want to change from ST to VT. Different from the earlier one. The earlier one just now, it was VT graph, changed to ST. Then at that time, we were looking at the value. But this time it's a bit different. It's the other way around. Okay, so this is March 19 P12. Let me see whether I have it wrong. March 19 P12. Right, so I've shown the answer here. You can try to have a look at it first. Okay, so I'll be gone for about 2 or 3 minutes because I need to go get some water. So in the meantime, you can just try the questions. All right. Okay, right. If you look at the question here, because you're talking about distance time and then velocity time, automatically you should relate it between velocity and displacement. So here you should see that the value of velocity would be equal to the gradient of your displacement time graph. Okay, so right now what you want to see here is the gradient of your SD graph, then translate it to value of your VT graph. So you divide it into 4 separate sections: section 1, section 2, section 3, and section 4. You want to look at how the gradient changes now. This part, you notice that this gradient is more and more positive. So the value should be more and more positive. And then you'll notice that this part here is still positive gradient, just that it's less and less positive. The value of your velocity should be less and less positive. And then likewise, you look at this part here, the gradient is negative, but it's more and more negative. So the value of velocity must be more and more negative too. And then lastly, you would see that, let me use a separate color. What color should I use? Accelerate. You look at this gradient, the gradient is negative, but it's becoming less and less negative. So the value should be less and less negative. The answer will actually be 8. Because if you look at the value of your velocity time graph, it's actually telling you the same story. Let me just match the colors. Or maybe I don't highlight it like that. I just use this. Okay, if you look at the first section here, the value of velocity is becoming more and more positive. But then the value of velocity for the second section is becoming less and less positive. And then lastly, the value of velocity here, sorry, use a different color. And then lastly, the value of velocity here is becoming more and more negative, similar to this one here. Gradient is more and more negative, so value is more and more negative. Then after that, you see the last section here, section 4, the value is becoming less and less negative, corresponding to gradient is less and less negative. Okay, so that's the logic for this one here.
Okay.
All right, so this is, I mean, when the first few times you try this, it may seem a bit tedious, but once you try a few examples, you more or less get the hang of it. This one will tell you how to find, I mean, if you're familiar with the method, it will become really fast. Okay, so in your school, I don't think your teacher taught you this. Did she? No, I don't.
No, I don't think.
Okay, so your teacher may have taught you a different method. So right now I'm teaching you another different method. It depends on you whether you are more familiar with the ones that's being taught by your KTJ teacher or the ones that's being taught by me. But for me, I would say that this is actually the most straightforward one. It looks a bit tedious, but it's actually the most straightforward one. Okay, right. There's also another way in which you can actually find the, sorry.
Can we finish like 5 minutes early today because I have a school thing to go to at 4:30.
Oh, okay, can, no worries, no
So you
worries.
can replace the 5 minutes the next class.
Yeah, sure, no worries, no worries. Okay, right. So I'll just move on, all right? Okay. The remaining part of your kinematics, the one that deals with the Suvet equations, the V equals to U plus AT and stuff like that. This one I'll probably leave it for next week because that one requires some very long explanation. So the remainder of this lesson, I'll probably just do some examples for you. Okay. All right. Okay, now there's also another method in which you can do this question here. This one may be a shortcut. Now, remember that over here we told you that the value of your VT graph is equals to the gradient of your ST. There are a few things that you can actually do. This is another method. You notice that this portion here, oh wait, let me use a separate color. You notice that this portion here, the gradient is 0. So therefore the velocity must be 0. So what you can do is that you look from these choices of graph, which of this actually corresponds to 0 velocity. Okay, you will notice that out of the 3 graphs, the only one that corresponds to 0 velocity is A. You see, this answer choice B, there's no 0 here when it should be 0. And then for answer choice C, although it gives you 0 here, it gives you 2 other additional points where it was 0. This part and this part. From this graph here, you're only supposed to have 3 points where velocity is 0. So the ones that only have velocity 0 at those 3 points was answer choice A only. So this one, this one, this one. Answer choice B, this part is not 0 when it's supposed to. Answer choice C, these 2 parts are 0 when it's not supposed to. And then you look at answer choice D. Okay, you look at answer choice D. For example, you have 0 where they're supposed to. Okay, let me just clear this off. If you look at answer choice D, you have 0 when you're supposed to have 0 here. Okay, but then there's one thing here that will then tell you something is different. You see this part here, this is opposite gradient. So therefore V should be, maybe you cannot see the wordings here, but let me write in a different color. You see the 2 points here, this one and this one is opposite gradient. Therefore, V should be opposite sign. So if you look at the answer choice D here, that one corresponds to this point and this point. You see, these two are actually giving you the same sign of velocity. When in the first place, looking at the graph that you have here, you're supposed to have 2 different velocities, same magnitude, no doubt, but they're supposed to be opposite sign because the gradient is negative, because the gradient is opposite. So although this one here, when you look at answer choice C, is giving you 0 where it's supposed to, but the velocity is having same sign here and here. It's supposed to be opposite. Okay, so you compare with answer choice A, it's giving you 0 where it's supposed to, and then it's giving you velocities at opposite directions, opposite signs. You see, this is velocity negative, this is velocity positive. Okay, so this is another way in which you can do so. All right, so there are many ways to do the same question. All right, okay, so this is one question here. Then after that, we'll just do some other questions. All right, the Suvet equations, the Suvet equation I'm talking about is this one. This one will take some time, so I'll just leave it for a while. I just do some of the common questions, basics first for you. All right, so if this one is okay, can you just look at page 51? Hey, no, not page 51, 71, I think. If it's not 71, then where is the question? 45. Wait, sorry, let me find the question. 51 or 52? 58, I think. Okay, right. 58, this one is another different question that involves graph drawing, page 58. Okay. Now the velocity of an object changes with time as shown. Which graph best shows you the variation with time t or the displacement s of the object itself? So this one, again, you see is velocity time. You want to change the displacement time. The two main variables are velocity and time. Sorry, velocity and displacement. So off the back of your mind, you should automatically relate it to this. Where again, we say that the value of velocity is equals to the gradient of your ST graph. So like for this one here, you just look at how the value of velocity changes. Then you use it to interpret the gradient of your ST graph. So you just do something like this, where we say that this one is positive, okay, and then this one is negative. All right, so this one is positive value, but how will I describe the values? Let me use a separate color. You see, going from here to here to here, this one is value of v less and less positive. But then if I look at the second part, how will I describe this? This one is value of v more and more negative. So correspondingly, you would say that the gradient of ST is going to be less and less positive. And then this one, the gradient of ST is more and more negative, right? This is what you want to see in the graph of ST. So which one is telling you that is actually supposed to be answer choice A? Because you see this one, gradient is becoming less and less positive. You see this part here will relate to this. And then you look at this part here, this gradient is negative. It's becoming more and more negative. Isn't it the same as this? Okay. So this is one way of determining it, as far as I know. Okay, right. So that one is okay. Then we just do some of the other examples then.
Okay.
All right. Right. So let me just see the questions that you can do. Question 4. No, you cannot do that one yet, but you can do question 3. All right, let's just go through this one. 3, 11. Can you get 88? Now let me just clear off everything, because I can't see the questions here with the screen like this. Okay, now I can see it. Okay, structure, probably page 10 would do. if I don't put this, 58 and then 45, 52. Okay, right, just have a look at page 52. Okay, page 52. Now, look at question 7. Two identical cars P and Q are traveling along a straight road. Car Q is traveling at twice the speed of car P. The brakes are then applied to both cars, producing the same constant deceleration. Which graph shows how the velocity v of each car varies with time t? Okay, this is again graph interpretation. What do you suppose is actually going to be the actual answer? But before you proceed, just look at the keywords here that you can see. Right, so some of the keywords here would be that you see that car Q is traveling twice the speed of car P. And then after that, they say that when the brakes are applied to both cars, you have the same constant deceleration. So the main key point was this one, and then 2. This one will tell you car Q is traveling at twice the speed of car P. That means VQ is 2 times VP. There's number 1. Then number 2 would be this one. Same constant deceleration. Okay. So it's same constant deceleration. That means same graph. Okay. Maybe I should word it this way. This one is constant deceleration. This one should be same constant gradient. Okay. So which of this is actually telling you that? Because you see the acceleration is actually VT, right? So acceleration, sorry?
Is the answer C?
Yes, correct. The value of acceleration is equals to the gradient of your VT graph. So if they tell you same deceleration, same constant deceleration, that means you have same constant gradient. So the answer is C. You see this one have same gradient. Okay, this is telling you you have same deceleration. And then over here you see that VQ is actually twice that of VP. So this is answer C. So this is one little graph that you can do. Okay, then maybe we just try our hand a bit on structured questions. Structured questions that deal with okay. Maybe we try page 95. Is it this one is 90? Structured question, page 95. Okay, let's go to structured questions rather than doing objective questions. Have a look at page 94. Okay, this one will talk to you about interpreting different directions. Have a look at page 94. You have a small block that is lifted vertically outwards by a toy aircraft as illustrated in figure 2.1. As the block is moving outwards, the string breaks at time t equals to 0. The block initially continues moving outwards and then hits the ground at time t equals to 0.9 seconds. The variation at time t of the velocity v of the block is as shown. Air resistance here is negligible. Okay. State the feature of the graph in figure 2.2 that shows that the block has constant acceleration. This one is November 2020 P21, so let me open up the paper for you. You already know that acceleration is given by the gradient of your BT graph. So which feature of the graph tells you that the block has constant acceleration, look at the gradient. The gradient is constant. So that one tells you you have constant acceleration because the gradient is constant. All right. And then after that, determine the height of the block above the ground when the string breaks. Okay, now this one you need to understand a bit of how the motion is. Just now they told you as the block is moving upwards, the string breaks at time t equals to 0. The block continues moving upwards and then falls and hits the ground at t equals to 0.9 seconds. So this portion here, let's look at this graph. Originally, you had a little helicopter like this that's moving with speed of 1.96 meter per second, and you were carrying a payload like this. This payload is also moving at 1.96 meter per second. But then after that, what happened was that they told you the string breaks. There's a breakage in the string. So if the string breaks, what will then happen is that your block, at the point of breaking, it was still moving at 1.96 meter per second. It will continue moving like this up to some sort of maximum height where the velocity becomes 0 meter per second. Okay, it will actually continue moving upwards because at the point of breakage, it was at 1.96 meter per second. It doesn't immediately go down to 0. It will still maintain with this speed, gradually reducing to 0 and maximum height. It will gradually reduce to 0 as it continues to move upwards before it eventually moves back down. Okay, so this graph that you see here is actually describing that. All right, you look at the area under your VT graph here, there's two different areas. This part here would be the part where you're moving up. The area here would be where you're moving up. And then this part here would be where you are moving down. Okay, so this is what's happening here. The area under here gives you the distance moving up. This area under here gives you the distance moving down. Maybe I should write this. This is distance moving up. This is distance moving down. Okay. So the question then asks you, use the figure to determine the height of the block above the ground when the spring breaks at t equals to 0. Okay. So right now they tell you that the block initially moves outwards and falls and hits the ground at time t equals to 9.0 seconds. This part here is already you hitting the ground. All right. So they want the height of the block above the ground when the string breaks. Okay, it'll be easier to visualize it like this. All right, this is where t was equals to 0 when you were moving at 1.96 meter per second. Then you continue moving upwards until you reach 0 meter per second here. This is you moving upwards. Okay? This was you moving upwards. Wait, let me find out where is. Oh, this was you moving upwards, represented by this area over here. Okay, then after that, once you have reached 0 meter per second, you've reached maximum height, you start to move downwards until you hit the ground. So when you hit the ground, this one was t equals to 0.90 seconds. Okay, the distance that you have moved going downward would be represented by this area here. Okay. So based on what the question wants, they want the height of the block above the ground at the time where the string breaks at t equals to 0. So basically what they want is actually this distance here. Okay, so you can see that you will need to take the difference between this distance and this distance to get the height above the ground. So you need to find the difference in the area, which is given here, right? You find out what's the distance moved outwards. You find out what's the distance moved downwards, and then you take the difference between the two. This will give you your height above the ground. All right. So maybe you take a minute to copy and write down the answer. And so this is one part. So that's why it's important for you to know for velocity time graph, when you see the area above and below the x-axis, they actually mean motion in different directions.
Okay.
Okay, right, so this part is okay. Now the block has mass of, okay, the block has a weight of 0.86 Newton. Calculate the difference in gravitational potential of the block between 0 and 0.9 seconds. So same thing as before, based on what they have here, what the question wants is the change in or the difference in GPE between 0 and 0.9 seconds. If you refer back to this little diagram that I've drawn here, t equals to 0 was here, t equals to 0.9 seconds was here. The difference in height is this one here, which you already found here. So to find the change in GPE is just going to be mg delta h. All right, but at the same time, you know that mg is actually weight. So you already have the value for the weight here. You just sub in and then you get the answer. All right, you get the answer as 1.96, 1.90 joules. And then the one will be your answer. Okay, so that is fine. Okay, then after that, the next one would be graph plotting again. Now on figure 2.3, sketch a line to show the variation of the distance moved by the block with time from 0 to 0.2 seconds. Numerical values of distance are not required. If they tell you from 0 to 0.2 seconds, you look at where they're talking about. They're talking about here to here. Okay. They're talking about this part of your motion. So they're asking you to produce a graph of distance versus time. But this is a graph of velocity versus time. You need to relate displacement and velocity together. So it is from this. So just now I told you value of velocity is the gradient of your ST graph. So same thing as before, you look at this one. This is all positive values. The value of V is less and less positive. So what you can infer from here is therefore gradient is less and less positive too. So straight away you can draw it like this. This is until 0.20 seconds. All right. This is from the interpretation that you've learned. Now, when you draw this one here, there is one other marking scheme point that they wrote. Please make sure that once your green colored line here hits the 0.2 seconds, the gradient at that point is 0. Because you see at 0.2 seconds, your velocity here is 0. Therefore, your gradient of st should be 0. Okay, there's the marking scheme point here. They say, okay, you must draw in such a way that it looks like it's 0 at 0.2 seconds. If you draw it something like this one we can clearly see that it is not 0. I mean, if you draw it, let me just draw an exaggerated case for you. You draw it like this now. This one is not going to be 0. It doesn't look like it's 0. The gradient seems to be a non-zero value. So if you do it like this, you won't get you will get a penalized mark. All right. It must be shown about horizontal such that the gradient is 0 because the velocity there is 0. Okay, so that one is okay. All right, so that part is done. And then after that, is there a question here that, oh yeah, this one also. Okay, there's this part here where they tell you a block of greater mass is now released from the same height with the same upwards velocity. Air resistance is negligible. Still explain the effect, if any, of the increased mass on the speed with which the block hits the ground. Okay, this one would probably be related to something here. Let me just see where is it in my notes. Under free fall acceleration. Okay, now there's something called free fall acceleration that you probably will have learned before. This one, just have a look at page 8 of your notes. Okay, page 8 of your notes. Okay, there's something about this part that I want to explain. Now, all objects, when you release it, it will fall to the ground because of the gravitational pull of the Earth. Okay, the force of gravity acting on the mass, pulling it down towards the Earth, is known as the weight. Basically, you have Earth here, and then if you have an object of mass m, you release it, it will move down towards the Earth because the Earth is exerting a force onto the mass. It's exerting a gravitational pull, a gravitational force on it. That gravitational force acting on the mass is what you know as weight, which is defined as W equals to mg. All right. Now, under the cases where only the weight is acting and air resistance is negligible, any object will always fall with the same uniform acceleration of 9.81 meter per second, regardless of their mass. Okay, don't bother about the volume and shape. This one is something else. Regardless of the mass of the objects. What do I mean by that is something like this. Okay, let me just go back to the example in your notes. All right. Yeah, maybe I just go through here. If you look back at the notes, if you look back at the last question in the worksheet, page 8, they tell you that you have a block of greater mass that's released from the same height with the same outwards velocity and resistance negligible and so on and so forth. So they ask you, what is the effect of the increased mass on the speed with which it hits the ground? Now, just consider this one first. If I have two objects, say M1, M2, and M3, I tell you that there is no air resistance. Okay, I tell you that there's no air resistance. This one maybe is worth 1 kg. This one is probably worth 10 kg. This one is worth 100 kg. And then they all have their own respective weights of W1, W2, and W3. Okay, so I release them all at exactly the same height. Okay, same same height. Okay, let me just write it as same height. All right. Now, what we will tell you is that without air resistance, all of these three objects will actually have the same acceleration downwards, which is going to be equals to g at 9.81 meter per second squared. Now, why do we say that is mainly because of this? You would have learned previously that F net is equals to ma. Resultant force is equals to ma. So if you were to apply it for the cases that you have here, F net for, in the case of object number 1, F net equals to ma. This one, the F net will be W1, the mass will be M1, the acceleration will be A1. Okay, now the weight will be M1 times G equals to M1 A1. If you look at this one, the masses will actually cancel off. So the conclusion here you get is that A1 is G. If you repeat this process for the others, F net equals to MA again. Your F net, your net force here being your weight W2, M2, A2. This one will be M2G equals to M2A2. You see the masses will cancel again, therefore giving you the conclusion that A2 is G. If you do the same thing for the last example here, F net again is equals to MA, W3 is equals to M3A3. So M3G is equals to M3A3. Again, you see the masses will cancel. So A3 is again equals to G. So you see, regardless of the masses that you're using, if there's no air resistance and the only force acting was just the weight, your acceleration will always just be equal to G at 9.81 meter per second squared, right? That's why here in the notes, I wrote it as this. For any object, if only the weight is acting and their resistance is negligible, then they will all fall with the same uniform acceleration of G. Okay, the explanation for this was actually this diagram that I written here for you. So this is true regardless of the mass of the object. Okay, you see here, even though I have the different masses, 1 kg, 10 kg, 100 kg, or even 1000 kg, it won't matter. I will still get the same conclusion that A is always going to be G. All right. The part about volume and shape of the objects here, this one is actually affected by air resistance. Okay. But because air resistance is negligible here, so volume and shape won't matter. All right. So this one here, the mass that I explained here is for these examples here. All right. So you can see here, if the masses are different, even though the masses are different, they are still going to have the same value of acceleration. They all will fall down with exactly the same rate. Okay, over here, they will all fall down at exactly the same rate. So from here, you can then infer that regardless of the mass, all three objects will actually hit the ground at exactly the same time. There will be no difference in the time that they hit the ground. Just because this object is, say, heavier, because of this having larger mass, doesn't mean it will fall faster. Okay, it's going to fall to the ground and hit the ground at exactly the same time as something which you say as lighter at 1 kg. Okay, it's going to fall down at exactly the same rate. It's going to fall down at exactly the same time when it hits the ground. So right now, when you look at this question here, they tell you a block of greater mass is now released from the same height with the same outwards velocity. Air resistance is negligible. Still explain the effect any on the increased mass on the speed with which the block will hit the ground. So the answer was just simply this. The acceleration of free fall is not dependent on the mass. There's actually no effect. It will actually fall back down on the ground with the same speed. Okay, or the answer was acceleration of free fall is unchanged, thus no effect. Okay, so this is what you can say to explain that. All right. So this one here is the same now, because although they say to you that is released outwards with the same outwards velocity, is released from the same height with the same outwards velocity, the same argument still applies. What I mean by that is this. This one here, just not that little, yeah, I think I better use it. Yeah. For this little example that you had here, this object here was moving up, and then after that, it moved down. Okay. Now the reason why it moves like this is because you always have that acceleration g pointing downwards. When you're moving from here to here, you're actually slowing down. Okay, your direction of velocity is here, your direction of g is in the same direction as your direction of g is opposite to the direction of velocity, so therefore you slow down, similar to what I just told you. Then you reach maximum height where v is 0, and then after that you start to move downwards. So when you start to move downwards, your direction of v is actually like this. Now when you compare with the direction of your g, the direction of gravitational acceleration is the same as your velocity direction. This part here is where you will speed up. Okay, so the fact is that your object slow down or speed up is due to g. All right, so the question says that your mass m1 changed to m2, is there going to be any difference in the time that it hits the ground? There's actually not going to be any difference. All right, because your acceleration still remains the same. All right, so that's the main KTL point that I just want to highlight here. There will be no change. It will not be dependent on the mass whatsoever. All right. Okay, so that is one part. Maybe we just do another one just to have a better idea. Maybe we just do something simple. All right. Let's just see for page 3 then. Okay, right. We just do something simple. I think you have something on at 4:30, right?
Yeah.
Okay. Maybe I just end this class maybe 10 minutes earlier so that you have more time to prepare. Then after that, I make up for it in the next lesson. Okay.
Okay.
Right. Okay. Just look at page 3. All right. The velocity of an electric car changes as shown. What is the acceleration of the car? Is there any trick to this question? Let me just answer this. A is the gradient of your VT graph, which would mean that it's actually going to be the gradient of this graph here. Now, is there any trick to this question that you can see?
I don't think so.
You see the units?
Oh yeah. Oh yeah, the answer is in meter per second.
Yes. Okay, so sometimes your P1 question, it may look straightforward, but then sometimes they've hidden some tricks behind that. So when you read this, you probably might have read it as this one is 50 divided by 10. This one you may have read it as 105 divided by 4. Then probably giving you 26.25 as the answer, but this is wrong because you still need to consider the kilometer per hour. So how do you change 105 kilometer per hour to seconds? This one is 105 kilometer over 1 hour. This one is one way of doing it. You change it to meter times 10 power 3. You change it to seconds. This one will be 60 minutes times 60 seconds. Okay, so this one will be 105 times 10 power 3 divided by 60 divided by 60 divided by 4. So you get 105 times 10 power 3 divided by 3600 divided by 4. You're gonna get the answer as 7.3 meter per second squared. Right, so the answer should be D. Okay, so this one is just one simple application of that. All right, so there's a trick to this. Even though the question looks simple, but there are some tricks that are hidden to it. All right.